Okay, so Susan, thank you very much for agreeing to talk to us, and you're going to talk to us about footprints of the Big Bang. Thank you very much.
I am indeed, and I trust that this time things will go better when I tried it than when I tried it last time. I will say that I did a Zoom presentation this afternoon and it went fine, so the signs are good. Okay, so today I want to talk about footprints of the Big Bang, two of which I actually show here on the title slide. And what I want to do is to explain how we know what we know. If you read any popular book on cosmology, it'll tell you all about the Big Bang and the events that took place in the first few minutes after the Big Bang, and it will all sound very convincing, but as scientists, we need to justify all of that narrative. And in cosmology, this is quite challenging. Obviously, we can't study the origin of the universe in a laboratory, although I must say a friend of mine, Alan Guth, once wrote a paper saying, entitled Creating a Universe in the Laboratory, but he also wrote another paper entitled Problems with Creating a Universe in the Laboratory. And we clearly can't go back in time to observe the creation of the universe. So how can we be sure of what happened 13.7 billion years ago? And I should say here that our level of certainty about what happened 13.7 billion years ago is actually quite recent. When I was when I was first in Sheffield, sometime in the 1990s, I don't remember exactly when, we had a talk by Malcolm Longair, who is a radio astronomer and an observational cosmologist, and he said that when he started doing cosmology in the early 1960s, it was a science of 2.5 facts. And there is a limit to what you can do with 2.5 facts. And in the 1990s, he went on to say in this talk that he thought the number had now gone up to about 8 facts. But what I hope to show you is that now the situation is much better, and our observations now strongly constrain our cosmological theories. It is no longer the case that you can basically make up your own alternative cosmology and you can be pretty sure that you can tweak it to fit the data. Now our data are strong enough that making up alternative cosmologies that work is a really challenging task. So we'll start, I think, by going through Malcolm Longair's 2.5 facts. And Malcolm's first fact was something that seems obvious. The sky is dark at night. And though this seems trivial, it's actually an important observation. And to see why it's important, think about the universe as it had been imagined more or less since the time of Isaac Newton. And Newton considered the universe to be infinitely large, because otherwise, under Newton's theory of gravity, it would collapse in on itself. And he considered that it would appear infinitely old, and there was no reason to believe that it was doing anything in particular, and specifically, it was not expanding. Now, if we take our infinitely large, infinitely old static universe, and we assume that within that universe, the galaxies are randomly distributed on a large enough scale beyond the clusters of galaxies and superclusters of galaxies that we see in the night sky, then if you project any line of sight in any direction far enough, you should eventually hit a star. And that is a problem, because it means that wherever you look, you should be looking directly at a star, and therefore that little patch of sky where your star is should appear to be as bright or have the same effective temperature as the average star. And the average star has a temperature of something like 3,500 Kelvin. So we should be completely fried by the sky. And this is self-evidently not true. So at least one of those assumptions must be wrong. If you make those assumptions, then this result follows. So the only way to make it not follow is to knock out at least one of the assumptions. In fact, we now know that two of the assumptions are wrong. The universe is not infinitely old, so light from distant stars hasn't reached us, and the universe is not static. In fact, it is expanding, and what that does is it causes the light from very distant objects to be effectively stretched to longer wavelengths, which means to cooler temperatures. So the light from a very distant star would not appear to be at a temperature of 3,500 Kelvin, but at a lower temperature. And in fact, it turns out that for stars, the fact that the universe is not infinitely old is the most important of these failed assumptions. But in order to prevent us from being fried by the cosmic microwave background, we also need the expansion. The second of Malcolm's facts was that the universe is expanding. And this is a fact which is approaching its centenary. Modern cosmology was born in the decade and a half between 1915 and 1930, both observationally and theoretically. On the observational side, in 1915, Vesto Slipher, the head of the Flagstaff Observatory, where Pluto would later be discovered, measured the Doppler shifts of so-called spiral nebulae and found that the majority of them had red shifts, that is to say they were moving away from us. In 1917 came the first evidence that these so-called spiral nebulae were not gas clouds like other kinds of nebulae, but actually external galaxies, and that was confirmed in 1925 by Edwin Hubble, and he followed up a few years later by making the observations that the speed of recession was proportional to the distance of the galaxy away from us, which demonstrates the expansion of the universe and is now known as Hubble's law. Meanwhile, on the theoretical side, 1915 saw the publication of Einstein's general theory of relativity, and in 1917, Einstein and Willem de Sitter produced the first cosmological solutions of general relativity. Those solutions were not in good agreement with the observations that were carried out in the 1920s, but between 1924 and 1927, first Alexander Friedmann and then Georges Lemaitre produced the modern cosmological solutions of general relativity, which I might say were initially poo-pooed by Einstein, and only when the theories were put together with the data, particularly the data from Edwin Hubble, did Einstein acknowledge that in fact Friedmann and Lemaitre had produced the most realistic solutions of his field equations when applied to cosmology. And here on the left is Hubble's original plot from 1929, and on the x-axis is distance, and on the y-axis is the recession speed as calculated from the Doppler shift. And you can see that although his data are not what you would call high precision, it is enough to demonstrate that there is a clear correlation between velocity and distance. That he fitted a straight line through it is basically just because that's the simplest thing you could possibly fit. Clearly, the scatter on the data are sufficient that if you wanted to fit something with a bit more wiggle in it, there's plenty of room to do that. This is no longer true. On the right, we have a modern equivalent to that plot, and this goes up to much, much greater distances, so great that in fact you have to correct for the fact that in Friedman's and Lemaitre's models, the Hubble constant, so-called, is not in fact constant over the history of the universe, and that plot appears to be a straight line because it's been corrected for that effect. The other thing I should say is that Hubble's value of his constant was very, very wrong. That value from that modern analysis is 73 kilometers per second per megaparsec. Hubble's original value was 550, so wrong by a factor of about 8. And it's interesting to note that in his 1931 paper, he took the view that that 550 had an uncertainty of definitely not more than 20% and probably not more than 10%. So what that tells you is that scientists can't always calculate their error bars correctly, and that fact has remained true over most of the history of measurements of the Hubble constant, to be perfectly honest. But that would be an entire different talk, so I'll just point out that the distance scale has needed many revisions over the century, or nearly a century, between Hubble's original measurements and what we have today. So if you run that expansion backwards in time, the natural deduction from that is that a long time ago, the galaxies were all in the same place, and that same place is now known, that fact is now known as the Big Bang, although that name dates from the 1950s. I should say that the actual place is not defined. It could be anywhere, or it is everywhere. Although we see all the galaxies rushing away from us, that does not mean that we are at the center of the universe. When you have an expansion such that speed is linearly proportional to distance, it's not difficult to see that it actually looks the same wherever you are. So if we all moved to some distant galaxy and we made the same measurements, we would see Hubble's law in the same way. This is only true for direct proportionality. If it had turned out that V was proportional to D squared or something, we really would have had to be at the center. But for a linear relationship, you can move the center anywhere you want without changing the relationship. It should be said that this was not immediately accepted, and that's because Hubble's value was much too big. That means the expansion is, his measurement of the speed of expansion is too fast, and that means when you run it backwards, all the galaxies wind up in the same place at much too young an age, and in fact you wind up concluding that the age of the universe is about 1 billion years, which is slightly embarrassing in 1931 because it was already well known by then that the age of the Earth was at least 3 billion years. So Hubble's law, taken at face value, implied that the Earth was older than the universe, and this is not really a credible proposition. And that's one reason why in the 1940s, Bondi, Gold, and Hoyle introduced the steady state model, where the universe expands but remains a constant density because of the creation of new matter, and therefore the steady state model is infinitely old and there is no problem. The problem with the Hubble constant remained true for nearly 30 years. It was only fixed by the work of Alan Sandage in 1958. So what about, that's Malcolm's first two facts. His 2.5 fact, only half a fact he explained in the 1960s because the evidence was not conclusive, although now it is, was that the universe is evolving with time. And this is the evidence that disproves that steady state model in which the universe would always look the same. If the universe is evolving with time, we expect it to look different at different times. Unfortunately, we can check that because if you have an object that is a long way away, the light from that object has taken a long time to reach us, and therefore we are seeing that object as it was a long time ago. So, for example, the Andromeda galaxy is about 2 million light years away. So if you look at a photograph of the Andromeda galaxy, the light that entered the camera to make that photograph left Andromeda 2 million years ago. That's not a long time by astronomical standards. It's a long time by human standards. 2 million years ago, Homo erectus had just about evolved. But you can, we can see galaxies that are billions of light years away, and those galaxies we are seeing as they were when they were much younger than our galaxy is now. So if the properties of any kind of astrophysical object change with redshift, that is to say, change with distance, that means that that class of objects is changing with time, and that means that the universe must be of finite age, because anything that is infinitely old will have settled down to a state of equilibrium where it's not changing. So some examples of this on the left, this is the rate at which stars are seen to form in galaxies, and you can see that rate reaches a maximum round about redshift 2, which corresponds to looking back in time about 10 billion years. So since the universe itself is only 13.7 billion years old, you are seeing those galaxies at redshift 2 as they were when the universe was only a third of its present age. And as you can see, there are data stretching back even further than that to when the universe was very young indeed. And you see a similar thing with active galactic nuclei, quasars and radio galaxies and that kind of thing. They similarly are most common in that same period between redshifts 1 and 2, sometime between 8 and 10 billion years ago. And these facts are not unconnected. Stars form from gas and dust in the galaxy, and active galactic nuclei appear active because gas and dust in the galaxy is falling into a central supermassive black hole. So both of these are connected to the gas and dust content of typical galaxies, and it makes sense that that would change with time. Another thing that tells us that the universe is expanding is the chemistry of the universe at the present time. Now, most elements are made in stars. The carbon that is the basis of organic chemistry is made in stars that are fusing helium, so evolved stars. The oxygen that you breathe is mostly made in supernovae, and the iron that makes your hemoglobin work in your bloodstream is made in a different type of supernova. And we can account for most of the elements in the periodic table in that way. The exceptions are the light isotopes between hydrogen and carbon, with the exception of helium-4. Hydrogen, the heavy isotope of hydrogen, deuterium, both the isotopes of lithium, beryllium, and both the isotopes of boron are very, very rare in the cosmos. And that's because rather than creating these elements, stars actually destroy them. Helium-4 is exceptionally stable among the light elements. And so all of these other isotopes, hydrogen-2, lithium-6, lithium-7, beryllium-9, boron-10 and boron-11, harbour a secret ambition to convert themselves into helium-4. And at the temperatures available in the cores of stars, they accomplish this quite readily, and therefore any lithium that is present in a newly born star is rather swiftly converted in the interior of that star into helium-4. So stars like the Sun make helium-4 quite copiously, but they don't make it copiously enough to account for the fact that in the universe as a whole, something like a quarter of the mass of the universe is helium-4, the other 3/4 being hydrogen, and all the other elements amounting to only a couple of percent. And we can understand the rare light isotopes by supposing that they are made when cosmic rays knock bits off carbon. But there is too much deuterium, there is too much helium-4, and there is somewhat too much lithium-7 to understand that. And our theories of nuclear physics demonstrate that we can produce these shortly after the Big Bang, when the universe was very hot and very dense, and nuclear reactions could take place at these high temperatures, which are equivalent to high kinetic energies. So on the left here is a plot showing how we calculate the abundances of these light isotopes to change with time over the first few minutes of the lifetime of the universe. That bottom scale is logarithmic, so 0 is 1 second after the Big Bang, 1 is 10 seconds, 100 seconds, 1,000 seconds, and 10,000 seconds. So this is the first 3 hours after the Big Bang, and you can see that we start off with mostly just protons and neutrons, and we end up with a mixture of elements, but mostly hydrogen, helium-4, deuterium, and helium-3. It's a log scale on the other side too, so those other elements, heavier elements, are formed only in very, very small quantities. And on the right, there is a plot which shows how the amount of each element you produce depends on the density of ordinary atomic matter in the universe. So as you assume higher densities, you make more helium-4, less deuterium, less helium-3, and more lithium-7. And so the lines represent calculations like the one on the left, and the yellow boxes represent measurements. And the key measurement here is of deuterium. If you look carefully, there is a tiny little yellow box there, and if you compare that with the blue line, you get an estimate for the density of the universe, which is given by the two pink vertical lines. And if you compare that with the estimate given by the cosmic microwave background, which is the blue hashes, you find that they agree extremely well. And they're also consistent with the measurement of helium-4, which is the yellow box at the top. There is a small fly in this ointment in that we consistently measure a lower amount of lithium than we would expect, and this is not well understood. We don't know whether there is something wrong with our nuclear physics or whether there is something wrong with our understanding of the workings of stars. So that is a problem yet to be solved. But I would say that the good agreement of the deuterium abundance with the completely independent measurement of the density inferred from the cosmic microwave background is a strong support for the Big Bang theory. I mean, there is no obvious reason, if the Big Bang Theory were wrong, why those two measurements should be anything like each other, and in fact they're in almost embarrassingly good agreement. So what is the cosmic microwave background, and why is it important to cosmology? Well, this is a property of a hot Big Bang universe that was actually predicted way back around 1950 by Ralph Alpha and Robert Herman. And the idea is that the very early universe is hot, it is dense, and because it is so hot, it is ionized. It consists of free protons, a few free helium nuclei, and free electrons. And this makes it opaque to radiation. Photons of light can only travel very short distances if they're traveling through a charged medium, because photons interact very, very easily with charged particles. And this, if a material is opaque to radiation, then any photons that are produced are repeatedly scattered by charged particles and exchange energy with the charged particles. And this produces what is known, confusingly to generations of students, as a black body spectrum. It's not obvious immediately why something that glows like the sun should be referred to as a black body, but the reason that it's called that is that this is true for any object that has no particular preference as to color, that it absorbs all wavelengths equally or with equal probability, and it emits all wavelengths with equal efficiency. And this black body spectrum is very closely related to the velocity spectrum of molecules in a gas, and it has this characteristic form that is shown in the top right. And the hotter your spectrum is, the bluer the light appears, and also the brighter it gets. And if anybody remembers old-fashioned radiant bar electric fires, you'll remember that when you turn them on, they started off by glowing a very dull red, and they finished up by glowing bright yellow, and that is because they were emitting an approximation to a black body spectrum. So we expect that in the very early universe, the photons would have this spectrum, would have this energy distribution. And now, as the universe expands, it cools down. And eventually, it will get to the point where protons and electrons combine to form neutral hydrogen. And the temperature of the universe at this time is about 3000 Kelvin. This is always referred to as the epoch of recombination, which is a bit of a misnomer because, of course, this is the first time that the protons and electrons have ever combined. So it's combination rather than recombination. Now, photons interact much less readily with neutral things than they do with charged things. So once the protons and electrons have combined to form neutral hydrogen, the universe quite suddenly, over a quite short period of time, turns from being opaque to being transparent. And that, as the saying goes, decouples this black body spectrum from the matter in the universe. And from then on, those photons just stream freely through empty space. And as they stream freely through empty space, because the universe is expanding, that expansion stretches the wavelengths of the photons. And that time when the universe cooled to 3000 Kelvin is at a redshift of about 1100. So as you stretch the wavelengths, you decrease the temperature by a factor of the redshift, or the redshift +1 if you're being fussy. And so what started out as 3000 Kelvin, which would be light predominantly in the infrared, you divide that by 1100 and you get 2.7 Kelvin, and this is in microwave and submillimeter radiation. So these are photons with typical wavelengths of a millimeter or so. And over the years, since since this radiation was discovered in 1965, it has been measured at many, many wavelengths, longer wavelengths from the ground, shorter wavelengths. The atmosphere is not transparent, and so you have to do it from space, and most precisely by the COBE satellite in the 1990s. And it is a beautiful black body. I mean, it is perfect over 4 orders of magnitude from wavelengths of 60 centimeters or so down to wavelengths of 0.1 of a millimeter. And the temperature is 2.725 Kelvin, which is pretty much exactly what one would have expected. That 1950s prediction said a temperature of the order of 5 Kelvin. So getting it right within a factor of 2 was a pretty good prediction. And this is essentially proof of the Big Bang model. This is a natural consequence of the universe having been opaque to radiation to create a black body spectrum at one single point in its past, to give that black body spectrum one single unique temperature. And so that comes about naturally in the Big Bang. It's very difficult to create in any other model. And this was really what killed off the steady state theory, because in the steady state theory, this radiation would have to be produced throughout the history of the universe, because the whole point of the steady state is that the universe looks the same at all times. And in that case, it would not have been a perfect black body spectrum, because superimposing a lot of black body spectra with all different temperatures corresponding to different redshifts does not make a black body spectrum. So the cosmic microwave background was a great success for the Big Bang theory. Or was it? The problem with that spectrum is that having a single unique temperature is frankly too good to be true. And the reason for that is quite simple. If you look at the black body spectrum facing due north, for example, those photons entering your receiver have been traveling since the universe was 400,000 years old. If you turn around and face south, you will see photons that have also been traveling since the universe was 400,000 years old. And clearly, those two regions of the sky cannot have exchanged photons during that time. And in fact, it turns out that because of the properties of the expansion of the universe, even if you look at regions that are separated by more than about a degree, there was not time for those regions to exchange photons and inform each other about their temperatures and reach an equilibrium state where they were all at the same temperature before the cosmic microwave background was emitted. So why is it all the same temperature? Well, you might argue, I've seen these maps from WMAP and Planck, it's not all the same temperature, and indeed those maps show hot spots and cold spots, but those temperature differences are only about one part in 100,000. And you really would not expect the early universe to be that constant in temperature. And if you say, well, it was an initial condition, the Big Bang all started at the same temperature, and that's the way it was, then you have the problem of explaining why it's not, in fact, precisely the same temperature. It's only the same to within one part in 100,000. So whichever way you go, that map is hard to explain in the classical Big Bang model. And that was one of the things which, in the early 1980s, led Alan Guth and Andrei Linde, who was then in Russia but has since moved to the US, to propose the theory of inflation, which Alan has described as a prequel to the Big Bang. It was like prequels in novel series. It was invented later, but in internal chronology, it takes place before. And inflation is the idea that for a brief period, very soon after the Big Bang, a tiny, tiny fraction of a second after the Big Bang, the universe was expanding very much faster than expected in the standard Big Bang theory. And the result of that is that if the universe grows in size by a very large factor in this tiny fraction of a second, the visible universe that we see today originates from a very much smaller volume of the universe before that inflation happened, and that very much smaller volume would have had time to exchange photons and settle down to the same temperature throughout. Inflation also solves other problems. It makes the universe geometrically flat, that is to say that in our universe, the angles of a triangle, if you draw it big enough, add up to 180 degrees, which is not necessarily true in general relativity. And it can also, in combination with quantum physics, explain why the temperature of the universe is not quite constant over the whole sky. So inflation is helps to explain these things that are not well explained by the Big Bang as it was originally conceived back in the 1940s. So these are just diagrams that show this. So here you have the effective radius of the currently visible universe as a function of time in seconds, and they're around 10 to the minus 35 seconds after the Big Bang. So that's 0.3401 second, very, very short time indeed. You see that the universe expands by an enormous factor, by 60 orders of magnitude. So that's a 1 with 60 zeros after it. And the consequence of that, as I said, is that we can understand why the night sky all looks the same temperature, and why the universe is geometrically flat, and where those tiny fluctuations in temperature came from. You may have noticed that this requires the universe to expand much faster than light to get to expand by that larger factor in only that short a time. And you might worry about that because doesn't relativity forbid you to move faster than light? And the answer is yes, it does, but no, that's not a problem, because relativity is talking about motion through space, whereas cosmology is talking about the expansion of space itself. So if you think of the universe as being a stretchy rubber sheet, the speed of light barrier applies to a model car that you roll across that rubber sheet, whereas inflation corresponds to grabbing hold of each side of the rubber sheet and stretching it. Different kind of motion. Now, of course, it's hard to see how you could find evidence for this process that happened only once, a very tiny fraction of a second after the Big Bang. One of the things it is expected to do is produce tiny ripples in space-time, tiny gravitational waves, and one way to look for evidence of inflation is to look for evidence of these primordial gravitational waves. You can't do that with gravitational observatories like LIGO because these waves have much too small an amplitude for LIGO to see them, but they do make characteristic swirly polarization patterns in the cosmic microwave background, which we might be able to see. And some of you might remember that a few years ago, an experiment claimed to have seen these, and there was much excitement, but unfortunately, that turned out to be a mistake. What they were seeing was polarization patterns caused by dust in the galaxy, and not by the very early universe. So, by the 1980s, we were reasonably happy about cosmology. And the models of Friedman and Lemaitre predicted that over time the rate of expansion of the universe should slow down because gravity acts to oppose the expansion. And so various groups set out to measure this because the rate at which it slows down tells you the density of the universe, and that was an interesting parameter that people wanted to measure. But in 1998, two groups attempted to do this using a particular kind of supernova, a type 1a supernova, which has the convenient feature that they all have pretty much exactly the same brightness. So just by measuring how bright the supernova appears to be, you can work out how far away it is. So these two groups did this measurement, and they found, rather to their surprise, that rather than slowing down, the expansion appeared to be accelerating. And you can see that in this picture on the right. It's easiest to see in the bottom picture where they've subtracted off the underlying linear expansion. What they were expecting to see is that dashed line that curves downwards, and even though the error bars on each individual point are quite large, it's pretty clear that they don't match that dashed line that curves downwards, and in fact they seem to want to sit on that thick black line that curves upwards. And this was bad news, because that black line corresponds to the reintroduction of something called the cosmological constant. And this had been invented by Einstein back in 1917, but Einstein had done it in order to prevent the universe from expanding, which he recognized that his model naturally predicted. And when subsequently it was found that the universe really was expanding, Einstein referred to introducing the cosmological constant as his greatest blunder. But now we have to put it back, and we have to put it back in a rather different way to try to make the universe expand faster over time. And the initial reactions to this measurement were not entirely happy. I remember talking to Alan Guth, because I was at Boston at the time, working at MIT with him, and standing in a bus and saying, "What do you think of this, these new supernova results, Alan?" And Alan said, "I hope they're wrong." But unfortunately for Alan's peace of mind, they were not wrong, and we now have far more data than those 1998 measurements, and they confirm that although in the past at very high redshifts the universe was decelerating as expected, since about redshift 0.5 the expansion has been accelerating. And this is exactly what we predict if the cosmological constant is indeed non-zero. And looking at the supernova data, which are plotted on the plot in the left in blue, together with other data, BAO stands for baryon acoustic oscillations, which means measurements using galaxy redshift surveys, and brown is the cosmic microwave background. You can see that they all converge on a conclusion that the cosmological constant, or dark energy, accounts for about 70% of the energy density of the universe at present, and matter accounts for only about 30% of the energy density of the universe. And this was not something that anybody had predicted before the observations. Moving back to the cosmic microwave background, as I said before, its temperature is not quite uniform. It varies by about 1 part in 100,000 over the night sky. And inflation, I told you inflation and quantum mechanics put together had an explanation for these variations. And you may know, you may have heard of the uncertainty principle, which is the statement that you cannot measure anything with absolutely precise accuracy. So quantum systems always have a certain amount of jitter. They have an intrinsic variability, and inflation explains the variations in the temperature of the cosmic microwave background as being caused by these quantum fluctuations, which get blown up from being quantum size to being macroscopic scale by the enormous expansion that takes place during inflation. And inflation also predicts that the dependence of the strength of the variation on the size of the hot and cold spots, and it gets that pretty much right. So this is the best evidence that we have at the moment that inflation is on the right track. Now, those characteristic sizes depend on many important cosmological parameters. They depend on the expansion speed, they depend on the density, they depend on the nature of dark matter, and various other things. And the great advance in observational cosmology over the past 20 years or so has been driven by detailed measurements of these temperature variations. And we generally display these as what's called a power spectrum, and you can see the power spectrum from Planck at the bottom left there. And these are expressed in terms of a mathematical thing called the multipole moment, which is basically measuring the angular scale. And this little animation by a cosmologist at Chicago called Wayne Hu shows you this, the size of the spots corresponding to the position of the pink bar as it sweeps across the plot. So you can see that it starts off at big spots and goes down to very small spots. And what you see in this spectrum is a number of peaks, and the biggest one corresponds to a preferred size for hot and cold spots of about 1 degree. And there are secondary peaks, you can see 2, 3, 4, 5, about 6 in the Planck data. And the second and third peaks are about 0.5 degree and 0.3 degrees. And the heights and positions of those peaks encode information about the properties of our universe. And to see the sort of thing that you would expect if the properties of the universe were different, I will show a few more of Wayne's animations. So on the left side there, the pink bar going up and down represents the density of matter in the universe, and the yellow curve represents what would happen if matter were all there were in the universe. And you can see that the position of that big peak moves towards smaller angles. The blue curve represents what happens if you compensate the change in matter density by introducing this cosmological constant or dark energy. And you can see that that means that the peak stays more or less in the same place. It moves a little bit, but not very much. So that affects the positions of the peaks. On the other hand, in the middle plot, this is what happens when you increase and decrease the density of dark matter in the universe. And you can see that that doesn't really affect the positions of the peaks, but it affects the heights of the peaks. The more dark matter there is, the smaller the peaks are. And on the right, this is the density of normal matter in the universe. And here, it affects the heights of the peaks, but it affects them in a rather different way from increasing the dark matter. What it tends to do is to make the odd-numbered peaks increase relative to the even-numbered peaks. So if you look at the second and third peaks as the pink bar moves up and down, you can see that their relative heights change significantly. So different features of this power spectrum respond to different features of our universe. We don't actually fit them all separately. What the people who work on this do is have an enormous and very complicated computer program that tries to fit all the parameters together. And what they come out with an awful lot of values of cosmological parameters, and you can combine this with other data to give us what we tend to call the benchmark model of cosmology. And this is somewhat dependent on assumptions you make, but if you assume a flat geometry, which is expected from inflation and is consistent with the data, and if we assume that the so-called dark energy really is a cosmological constant and has the properties of a cosmological constant, then you can extract from that things like the Hubble constant. You get 67.4 kilometers per second per megaparsec. The density of normal matter in the universe, which in my pie chart is given by the little green slice of 5% of the total energy density of the universe is atomic matter like you and me. The red is the dark matter, and that corresponds to a little over a quarter of the total energy density of the universe. And the rest of it is made up by this mysterious cosmological constant or dark energy or whatever you want to call it. What I'd like to draw your attention to is the error bars on those numbers, the plus or minus bits, and you can see that they are of the order of 1 or 2%. And this is a remarkable achievement. As recently as the 1990s, those numbers had uncertainties that were a factor of 2. So we have reduced those uncertainties from a factor of 2 down to a couple of percent. So that is what I meant when I said that in the 21st century, observational cosmology has moved from being very, very rough and ready to being a precision science with real experimental measurements that theories have to explain. So you might say that over the last 20 years, we have really acquired a good understanding of the universe. This is not true. We know that dark matter comprises about a quarter of the energy density of the universe. We have a good idea of what its properties have to be in order to make it behave in the right way. We have no idea what it actually is. If it is a particle, it is not a particle that is present in our current standard model of particle physics. We have absolutely no idea what the dark energy or cosmological constant is. Dark matter, we've got a pretty good idea of what its properties are. Dark energy, we simply do not understand. The natural way of interpreting it is as a quantum mechanical energy of the vacuum. And if you do that and you attempt to estimate how big that cosmological constant should be, you get an estimate that is wrong by 110 orders of magnitude. That is to say, it is a factor of 10 to the power 110 larger than the observed value. And this, well, Steven Weinberg, the Nobel Prize winner, has described this as the worst failure of an order of magnitude estimate in the history of science. And it's hard to disagree. We normally expect that kind of estimate to get us to within a factor of 10, not to within a factor of 10 with 110 zeros after it. And the other problem that we have is that initially, as we reduced these error bars, everything looked beautifully self-consistent, and the theoretical cosmologists were patting themselves happily on the back. And over the past few years, this happy agreement has started to break down a bit. The high precision results from different methods are beginning to show disagreements which look trivial compared to the situation in the 1990s, but because our error bars are so much smaller, they are actually not trivial at all. And most noticeably, there is a strong tendency for traditional measurements of H0, that is to say, measurements that Hubble would understand, where you plot speed of recession against distance, to differ from measurements based on the cosmic microwave background. And those of you who have good memories will have noticed this, because back about slide 3, when I showed a modern Hubble plot, the value of H0 I wrote was 73, and a couple of slides ago, when I told you what you get from the Planck data, the value that I told you was 67. So they're about 10% different, with error bars of about 1%. So that is a significant disagreement. And here's a plot that was made quite recently, and this shows the problem. So up at the top there are measurements that rely on properties of the early universe, and they consistently get something of order 67. And at the bottom are measurements made using velocity equals h0 times d. And the problem with that is that you have to calibrate your distance measurements. That was where Hubble had problems. And there are different ways of doing that calibration, which shift it about a little bit. So that's why the 4 points at the bottom are in slightly different places. But all of them tend to get measurements of the order of 73, and 73 is different from 67. And this discrepancy, when it first surfaced, it was just assumed that one of the methods being used must have a systematic error that was causing it to produce a high value or a low value. But it's now persisted for several years, and it's found in multiple different analyses, and it's getting harder and harder to dismiss it as just due to measuring error. So when we analyze the cosmic microwave background, we make certain assumptions about the underlying cosmology. Maybe those assumptions are wrong. So is this the first evidence for a cosmology that is more complicated than we assume? For example, is dark energy not actually a cosmological constant, which, as the name suggests, is constant with time, but something which has changed over time, and this is why measurements taken from the early universe get different results from measurements taken using the local universe. So to summarize, I hope I have convinced you that the evidence for the hot Big Bang model of cosmology is very strong. We are not just making it up as we go along, and we are not just letting the theorists do whatever they feel like. With modern data, alternative models either do not fit, or they are made to fit by being very, very close mimics of our standard models. So there are some so-called brain cosmologies that invoke extra dimensions, which make predictions that are very, very similar to the predictions of the standard hot Big Bang general relativistic model. I hope I've also convinced you that over the course of the 21st century, the last 20 years or 22 years, if you go back to 1998 and the supernova results, observational cosmology has become much more precise, which means it is much more powerful in constraining theories. And that precision is now beginning to throw up some possible difficulties with our standard model. And if you add those possible inconsistencies to the things that I mentioned a couple of slides ago, that we do not understand, the nature of dark matter, anything at all about the dark energy, then you can see that cosmology is far from being a done deal. There is a great deal that we still don't understand, but our measurements are improving all the time, and I have hoped that within the next decade or so, some of these problems will be solved and our understanding of our universe will be enhanced still further. Thank you.
Thank you very much, Susan. Paul, yes, a lot to take in there. Yeah, I spotted something on your slide called Holy Cow. Is it one of the methods of
yes, that is one of those acronyms where I am pretty sure they thought of the acronym first and then spent some time in a darkened room trying to figure out how they could make it into an acronym.
Yeah, because the story of the cosmic microwave background and discovery is a fascinating one in itself, isn't it? That's probably a whole talk in itself.
That's a whole talk in itself.
Involving pigeon poo and all sorts of things. And they found something they weren't looking for, and it was noise, wasn't it? So
it has to be said that that was a discovery whose time had come. If Penzias and Wilson had said, stuff it for 3 Kelvin, I'm not worrying, Roland Wilkinson would have discovered it within a couple of months.
Yeah,
they were building a detector to do it.
Yeah, because they were intentionally looking for it.
Yes.
And it was only when they spoke to each other they went, "You found what we're looking for."
Yes, apparently, Bob Dickey, who was the leader of the group, Penzias was speaking to somebody at a conference and was told to call Bob because he might have an explanation for his funny noise. And Bob apparently turned from the telephone and said to all his postdocs and graduate students, "Boys, we've been scooped."
Yeah, fantastic story. Yeah, really good. Right, anybody got any questions?
I have, please. Susan, I struggle with the galaxies. I believe they were formed about 400 million years after the Big Bang. And I struggle to understand how they were formed.
It's basically it's basically an arms race between gravity and the expansion. And in fact, dark matter is critical to the formation of galaxies. When you do a course on introductory cosmology, which I have taught for some years, you find that you can only start to grow galaxies once the universe stops being dominated by the energy of photons and becomes dominated by matter. And that occurs at a redshift of about 3,000 or so. And for that period, from that period on, you can start, things will start falling in towards small changes, small variations in the density of the universe. So if there's a bit of the universe that is slightly overdense, stuff will fall into it. And so you'll get a gradually increasing contrast in densities, and that will eventually create galaxies. But this only works if there is dark matter, because at redshift 3000, all the ordinary matter is still charged, it's free protons and electrons, and those interact with the photons so strongly that they are prevented from collapsing to form galaxies. So the fact that galaxies exist is actually evidence in favor of there being such a thing as dark matter. But nowadays, this is actually very accurately simulated, and there are some lovely movies around produced by the Virgo collaboration which show how you can simulate a very, very smooth distribution similar to the cosmic microwave background, and if you let the simulation run, you eventually get galaxies and clusters of galaxies. They're really pretty simulations.
Okay, thank you.
Okay, any more?
Yeah, I've got a question, Dave and Susan, if I may. Again, something I've often struggled with, and maybe I'm just missing something obvious here. But as I understand it, inflation, the size of the universe when inflation ended was of the order of several millimeters or so, if I understand that correctly. What we see now as the edge of the observable universe is 13.8 to 14 billion light years away. But in the time that light, when those photons were emitted from the early universe, the universe itself was very, very small, relatively speaking. So how has it taken 14 billion years to travel that relatively short distance from when the photons were originally emitted, if my question makes sense?
Yep, it does make sense. Basically because the expansion rate was very much faster in the past. And so it's a bit like if you imagine two trains in standard Einsteinian fashion, let's have trains, and they're initially close together, and then you make them drive away from each other, and on the roof of one of the trains there's a pigeon which starts to fly towards the other train. It will take it, even though when it started off the trains were close together, if the trains are travelling only slightly slower than the pigeon can fly, it'll have to travel more distance before it lands on the other train. And that's basically what it is. The expansion of the early universe is only marginally slower than the speed of light. And so by the time the light reaches where the receiving galaxy was when it set out, the receiving galaxy has moved significant distance further on. And it takes it 13 billion years to catch up, basically.
Right. Thank you. I'll have to think some more on that, but thank you. That was quite a clear explanation. Thank you.
Anybody else?
My microphone's working.
Just about. You can just about hear you, Julian.
Pardon?
Only just hear you.
Oh, right.
Shout!
Well, let me turn up my microphone if I can. Well, anyway, if you can hear me.
Yeah, that's better.
Alan Guth was originally looking for magnetic monopoles when he tripped over inflation, wasn't he? Are they still something that cosmologists are looking for?
Not if inflation is right. It is indeed true that one of the things that was worrying Alan was that magnetic monopoles are caused by the collapse of the grand unified theory, which is what we expect particle physics to look like at very, very high energies, into the standard model of today, where you have different forces. You have the strong force, the electromagnetic force, and the weak force. And this is a bit like crystallizing a solid from a melt. And depending on the axes of the crystal that you produce are randomly oriented. And over long distances, in a crystal, you get dislocations in the crystal lattice. And the equivalent thing happens in the grand unified theory, that the way in which it collapses into the different forces can be different in different places. And the equivalent of those crystal dislocations is distortions in space-time, which appear like very, very massive structures. So in 2 dimensions, you will get what's called a domain wall, and a magnetic monopole is a one-dimensional fault in the structure of space-time. And because they are formed at very, very high energies, that means that they effectively have very, very high masses. And you expect, because this is a failure of long-range order, you expect to get 1 per horizon size in the early universe. And because the horizon in the early universe was very much smaller than the horizon at the present day, if you do the calculation with the classical Big Bang, you find that the modern universe should be totally dominated by magnetic monopoles. And in fact, worse than this, the modern universe should not exist at all, because the magnetic monopoles are so massive that they would cause it to collapse back into a big crunch after a few minutes of its existence. So we would never have formed. So one of Alan's motivations for introducing inflation was to dilute the density of magnetic monopoles. So if you believe inflation, all of our present visible universe formed from within a single horizon distance before inflation. And inflation is cunningly timed to take place after the collapse of the grand unified theory. That's why it's 10 to the minus 35 seconds and not 10 to the minus 45 seconds. And so, because you expect about one magnetic monopole per horizon distance, under inflation you expect at most one magnetic monopole in the visible universe. So you can look for it if you like, but your chances of success are not high.
Thank you very much.
Okay. Right, any other questions, folks? No? Okay, well, thank you very much, Susan, for the talk. I didn't understand a lot of it, but yeah, it's certainly a lot in there to take on. So so we recorded it, so we can have a look again if we want to catch up on some bits. So thank you very much for that. After the discussion at the beginning about the planets, we've got Martin Lewis talking on the 7th of July. So depending on how long his talk is, we'll try and fit something in about taking images of the planets and things for that. Is that okay? Yes, on the 7th of July, because Jupiter's coming to opposition on the 14th and Saturn on the 20th. So that seems about right to get them at the best. Okay? So we'll try and do that.
Splendid.
Yeah? Okay? So I'll put that in the calendar and yeah. All right. So thanks so much, everybody, for coming in again tonight. Thanks to Susan for the talk on cosmology that you all asked for all those weeks ago. So
thank you, Susan. Thank you, Dave.
Thank you,
Very nice.
Susan.
Thank you,
Thanks,
Susan.
Susan. Great,
Thank you
great
very much.
presentation.
the internet connection was much better this time, so thank you. Okay, so keep safe, everyone. Keep well, and keep
Yep.
looking up.
Absolutely.
Cheers, Dave.
Okay.
Bye, everyone.
Take care.
Bye.
Bye.